Hypothalamus Artificial Intelligence, HI. Digital transformation powered by autonomous and intelligent algorithms in real time. Presents its solutions based on artificial intelligence for decision-making for natural gas supply chain optimization. HI has the support of its technological allies, General Algebraic Modeling System, GAMS, and IBM, producer of C-PLEX Optimization Studio. Both products are incorporated into HI's artificial intelligence solutions. Optimization of natural gas networks. There are many applications of mathematical models of optimization of natural gas system networks. Basically, for all applications the same model is used, from different points of view, which entails adjustments in the mathematical modeling. Some of the applications are: natural gas market simulation, natural gas market and system regulation, real-time optimization of natural gas pipelines, and optimization of natural gas systems. The Natural Gas Market Module, NGMM, is the component of the USA National Energy Modeling System, NEMS, that represents the North American natural gas transmission and distribution system, and market. The module is a quadratic program that maximizes consumer plus producer surplus minus transportation costs. The consumer surplus represents the amount of money saved by consumers, who would buy natural gas at a given price but are able to obtain it at a lower one. The producer surplus represents the added revenue of suppliers, who could sell natural gas at a lower price but are able to charge a higher one. Therefore, by maximizing this combined surplus, and subtracting transportation costs and subject to balance and capacity constraints, the model arrives at an equilibrium price for the market. The image presents the NGMM natural gas pipeline network. Purdue University's SUFG, State Utility Forecasting Group, has supported experts from the Indiana Utility Regulatory Commission, IURC, since late 2001, with the goal of examining the impact of new electricity generating facilities within the gas system. The model determines the mix of purchasing, transportation, and storage decisions of local distribution companies, LDCs, which minimize the sum of purchasing, transportation, and storage costs over a 60-month planning period, subject to the following constraints. Consumer demand at demand nodes must be met. The flow capacity of gas pipelines should not be exceeded. Storage capacity limits of storage sites should not be violated. The amount of gas transferred from one pipeline to another cannot exceed the capacity of the interconnection, and long-term purchases and dispatch contracts. The image presents the network topology of the gas modeling system. Real-time optimization of natural gas pipelines. Nowadays, natural gas is one of the primary energy resources employed in many sectors, and it can be regarded as a bridge fuel in the decarbonization process. The transport of natural gas relies on a complex infrastructure, which needs to be properly managed to minimize energy consumption and CO2 emissions. The performance maps of the gas turbine-driven compressors have been linearized using the convex hull approach. The model includes all the technical limitations of the gas turbine-driven compressors, and it can handle flow reversals on all pipes. Moreover, it is suitable for cyclic networks. The MILP model is applied to a case study with 4 compressor stations, each containing multiple gas turbine-driven compressors, and a cyclic network consisting of 29 pipes. In this case, the MILP model was used to optimize the 24 hours of unit commitment, with time resolution of 30 minutes, and sections of a maximum length of 200 kilometers. The continuous variables of the MILP are 18,816, the binary variables are 1,421, and the constraints are 43,429. The optimal unit commitment and load of the gas turbine-driven compressors, GTDC, is shown in the figure. The solution uses only one GTDC of station S1, 3 GTDCs of different sizes in stations S2 and S3, while station S4 is always in the bypass mode. The optimized solution features an objective function which is 7% lower than a preliminary solution found by fixing the commitment of the GTDCs S1 S3, optimizing only the loads. Optimization of natural gas networks based on stochastic optimization. This model provides a review on the most relevant research progress related to the steady-state operation optimization models of natural gas pipelines as well as corresponding solution methods based on stochastic optimization algorithms. The existing operation optimization models are mixed integer nonlinear programming, MINLP, MODESL, involving a non-convex feasible region and mixing of continuous, discrete, and integer optimization variables, which represents an extremely difficult problem, to be solved by use of traditional monolithic optimization algorithms. However, no reference is made to advanced methodologies using large-scale optimization methodologies. A schematic of a natural gas transmission system can be conceptualized based on three subsystems: gathering pipelines, transmission pipelines, and distribution pipelines. The images shows a gas pipeline network composed of a tree and a cyclic network. The real-time model can handle differentiated electricity costs by time of day, or by load block. Using this way it take advantage of low rates, or low marginal costs, in periods of electricity low load. A gas pipeline is a pipeline that allows combustible gases, natural gas, liquefied petroleum gas, to be transported on a large scale and over a long distance. Pipelines planning and scheduling. The optimization model includes the following types of nodes: production fields, consumption center, natural gas demand nodes discriminated by demand sector, among which are industrial, vehicular, electricity generation, commercial, and residential, and ports and terminals that can receive and/or send LNG. It is associated with liquefaction and/or regasification plants. Those interested in learning more about modeling gas piping systems are invited to watch the video. Oil pipelines optimization. Electricity and natural gas integrated modeling. High power integrates the following models. High electricity supply chain optimization supports decisions in the electricity supply chain, in terms of sectoral planning and business generation. High smart grids optimization supports the decisions of the various agents involved in the smart grids business. High natural gas supply chain optimization supports the decisions of the actors involved natural gas supply chain, at the level of sectoral planning and business generation. The following is the topology of high power. Hydraulic system physical modeling. High water corresponds to a general model that includes all kinds of hydraulic components, reservoirs, hydroelectric power plants, rivers, overflow channels, connection points and pumping stations, demands, like irrigation, aqueducts, environmental, industrial. Components can be freely linked to form any topology, like pumping storage systems. Hydroelectric power plants are modeled independently of reservoirs, so plant-reservoir connectivity must be established. The regulation capacity of the reservoir is simulated in detail, so such a simulation consistently represents the dispatch of the power plants, considering their ability to regulate the multi-annual, annual, hourly water resource. Electric system physical modeling. Electrical connectivity is carried out through a network of circuits and bars that integrates different types of installations, power plants, like hydroelectric, thermoelectric, coal, wind, solar, biomass, places of demand, like industrial, cities, regional interconnections and energy storages. High power includes the simulation and several types of renewable energy sources and energy storages. For each type of electrical asset, high power includes the exact equations for simulation. Natural gas system physical modeling. High gas describes the process of supply and demand of natural gas. From this point of view, its integration with the electricity system determines the economic equilibrium electricity-gas markets. The entities of the natural gas system are: node, connect the gas system installations; production fields; consumption zones, discriminated by sector, example, refineries, heavy industries, residential, vehicular, and commercial thermoelectric power plants; transport systems, I, pipelines and 2, multimodal transport systems using vehicles, pumping stations, compress the gas to transport it, and ports, receive and ship liquefied natural gas, LNG, and have gas storage capacity. Connectivity between the electricity and gas sectors occurs through the demand for natural gas for use in thermal plants, and the substitution of the demand that can occur between gas and electricity. High power, Autonomous optimization software for energy sector enterprises. It is an optimization decision support system aimed at agents acting in the energy sector, understood as the union of electricity, natural gas, oil, bio-renewable sources, and new non-conventional sources. For more information, interested parties are invited to watch the video. High power use case: Oil Express natural gas field exploitation planning. At the end of the last decade of the last century, Oil Express, a global natural gas company that operated several natural gas producing fields in multiple countries, asked High for support to define a natural gas field exploitation planning strategy, using highly complex mathematical models, to analyze the entire decision-making environment. The challenge was to develop a model that supported the decision-making regarding the exploitation of natural gas field and its impact on Oil Express finances. Solution: design and implementation of a DSS for management of natural gas oil field strategic decisions like the exploitation period. The models included in the DSS were: electricity and gas economic dispatch simulation, optimization of the gas trading decisions, optimization of the financial and fiscal decisions, and financial simulation of the gas buyers. Result: the SHTG model, hydrothermal and gas system, the first version of the actual high-power model. Based on the high power, Oil Express makes its decisions that produced successful results that led to higher profits by delaying the exploitation of the gas field for an economically more convenient time, due to the non-sustainability of the market. People interested in the case can watch the video, Oil Express, Natural Gas Field Exploitation Planning. Oil and gas pipelines nominations and bilateral contracts. The nominations are the agreements made by the carrier and dispatcher to transport oil, natural gas, and petroleum products, using pipelines. This process normally occurs within a long, or medium-term contract, between the transporter and the dispatcher. In turn, the contract of the dispatcher, who can be a distributor, or a large consumer, is backed by contracts with end customers, and this process determines the demand for transport services that must be attended by the transport system operating company. Short glossary. Nomination: a request for a sender's transport service. Nominated quantity refers to the volume that the sender requests to be transported from a point of receipt and delivered to a certain point of delivery. For a period of nomination, this must be authorized by the carrier. Nomination period: this is the period for which the dispatcher submits its transport nomination request. Cycle: subperiods into which the nomination period is divided. For example, days, weeks, fortnights, etc. Period represents the period to be nominated, month, week, day, or another period agreed between carrier and dispatcher. The image shows a oil and gas pipelines nomination example. Mathematical modeling. The nominations have several relationships with mathematical modeling, namely: short term, determine the demand for transport services that the carrier has accepted and authorized, normally assumed as an input data that is not affected by the real-time or short-term model. Medium term, tactical planning, depending on the agreements between carrier and dispatcher, the medium-term model, of the order of months, week, days, can adjust the nominal transport plan to optimize the economic benefits and to improve the technical conditions of the operations, and long-term, strategic planning. This modeling can be related to long-term contracts. They can be used to accept the contract, verifying the required transport capacity, and definition of the price, or the marginal costs associated with attending the long-term contract. At the end of the last decade of the last century, Oil Express, a global natural gas company that operated several natural gas producing fields in multiple countries, asked High for support to define a natural gas field exploitation planning strategy, using highly complex mathematical models, to analyze the entire decision-making environment. The challenge was to develop a model that supported the decision-making regarding the exploitation of natural gas field and its impact on Oil Express finances. Oil Express, Natural Gas Field Exploitation Planning. In 1997. Analysis of the gas market for the electricity sector. The main study carried out with high power was the analysis of the national gas market for the electricity sector. This is due to no alternative markets for natural gas other than national electricity generation. Pressure from the electricity regulator to sign contracts by generators and producers of natural gas for the purchase and the transportation of natural gas to give firmness to the electricity sector. Oil Express fundamental hypothesis: if the gas market is not sustainable, it makes no sense to sign bilateral contracts with electricity generators and to invest in extracting the natural gas, and the optimal strategy is to wait for the right moment in the future. The analysis was carried out using take-or-pay contracts as a basis. The take-or-pay (TOP) is a contractual clause requiring the buyer to take the delivery of a specific amount of goods or services from the seller or pay a fine if they do not. Thus, it protects the seller against potential losses if the buyer refuses to complete the purchase by a particular date. A top clause is common in energy industries, including oil, natural gas, mineral, and coal, seeking significant investment. It is also called the kill clause. The contract is normally signed before the companies start oil, natural gas, minerals, or coal exploration. Therefore, it is a type of offtake agreement. A top clause is common in energy industries, including oil, natural gas, mineral, and coal, seeking significant investment. It is also called the kill clause. The contract is normally signed before the companies start oil, natural gas, minerals, or coal exploration. Therefore, it is a type of offtake agreement. Fuel supply contracts directly affect dispatch. In general, a contract has the following components. A percentage of the maximum consumption is purchased in the take-or-pay mode. The surplus over the take-or-pay is purchased under the pay-as-you-go modality, and there is a rolling period to consume the take-or-pay part. Given the seasonality of prices in the electricity sector, the model included TOP with a rolling period, which gives flexibility to the buyer to accommodate their physical purchases. But it complicates the generator decision-making process. To stimulate the natural gas market for the electricity sector, government institutions conducted a reference study. This study was taken as a reference to analyze the market using the SHTG model. The main characteristics of the study was: the rolling period was 6 months. 10 plants were considered for take-or-pay contracts with an installed capacity of 2,813 megawatts. The take-or-pay percentage was 30% for the plants of the center and 70% for the plants in the border, and the electricity dispatch planning model used by ISO operator was adapted to represent the impact of TOPS. The table presents the summary of the characteristics of the scenario studied by the regulator to stimulate the signing of contracts in the natural gas market. The percentages of TOPS fixed do not come from an optimization model, they were perceptions of what should be. The chain of qualitative effects, which derive from top contracts, is relatively easy to foresee. The bid price of the thermal plants to the spot market will go down. This is because they have turned the variable cost into a sunk cost. In the extreme, it could reach zero. This will lead to an increase in the dispatch capacity of thermal plants, and the fall in spot prices. But quantitative effects, they're not intuitive, they can't be calculated with an Excel spreadsheet. As the volume of natural gas contracted through TOPS increases, it can be expected that hydro plants will lose share, thermal plants will gain participation, and the spot price go down. It is clear an economical resource, but not 100% reliable, hydroelectric energy, is being exchanged for another more expensive but more reliable, thermal energy. It should be considered as a risk premium. From the point of view of income, we have revenues from hydro generators will decrease, and the change in the income of thermal generators cannot be evaluated a priori. Therefore, a mathematical model is required to evaluate quantitatively the natural gas market. Modeling take-or-pay contracts. To carry out the study, 5 cases were implemented to consider the top modeling. The following is the code associated with the modeling and description. No top, no contracts. Libre, optimized contract generation. Equations are included in the dispatch model, high power, to accurately represent top contracts. Rodante, minimum rolling generation. The minimum generation of the thermal plant is forced during the rolling period, to ensure compliance with the contract. Mensual, minimum monthly generation. The minimum monthly generation of the thermal plant is forced, to ensure compliance with the contract. More restrictive than the previous one, and MWKTE, fixed generation at the base. The thermal plant is forced to generate in the base, permanently, to ensure compliance with the contract. More restrictive than the previous one. All forced generations can be implemented with an economical dispatch model, without requiring modifications to the model. All these imply losses for thermal plants, when the marginal costs of electricity are below the variable cost of top. Top contract modeling implies dividing the thermal generation in GT0 thermal generation with cost equal to variable OM costs excluding fuel cost. Typo 0, limited by top contract, and GT1 thermal generation with cost equal to variable OM costs plus fuel cost. Type 1, non-top contract. GT, the total thermal generation, must be equal to GT0 plus GT1. There is only one appropriate way to study top contracts, and in general any bilateral contract. Model the operations and the financial transactions as they are described in the contract. Approximations to this modeling will only bring economic losses for the generators and for the society. For example, trying to adapt an economic dispatch model, by parameterizing the dispatch of thermal plants, will bring negative consequences for all market agents. All forced generations can be implemented with an economical dispatch model, without requiring modifications to the model. But all these imply losses for thermal plants, when the marginal costs of electricity are below the variable cost of top. To quantify the financial impact of take-or-pay contracts, we can consider the estimated operating income for generators, defined as the marginal cost, a proxy of the spot price, multiplied by the generation. Since the spot price goes down due to the top, the highest value reference is the market with no contracts. In this case, for simplicity, the post-optimization financial impact has been evaluated, using the resulting dual variables as a reference. However, it should be noted that high power can solve an PEC, mathematical problem with equilibrium constraints, problem in order to convert the financial impact into part of the optimization model, and thus obtain a more accurate view of the health of the market. Scenario aggregate economic results. Following the logic, the most economical option is not to consider the top contracts. When including the top, a risk premium must be assumed, which could be established as the difference between optimized contract generation and no top contracts. In this case it implies 26% of cost overruns. The last three cases involve overcost due to the poor quality of mathematical modeling. As poor quality increases, cost overruns increase. It must be interpreted that if we implement low-quality models, this will translate into more expensive operations, which will pay someone in the market. The first candidate is the user of the models. The effect for hydraulic generators, which generate less, and receive less remuneration for each MWH generated, the negative effect is evident. For thermal generators with top, the increase in generation could be produced a higher operating income. The impact can be summarized as: top contracts as proposed adversely affect the aggregate of all generators, and when mathematical modeling practices are incipient, this will negatively affect the market. A good way to present the financial information is the accumulated curve of estimated operating income over the entire planning horizon. The graph shows operating income of hydraulic generators. These graphs presented the aggregation of all generators, but they exist for each individual generator. In the case of this hydro generator, paradoxically its financial health does not depend on its actions, but on that of other agents. If thermal generators assume a rational position, the financial health of the hydro generator will not be affected. But, if they assume an irrational position, ignoring mathematical laws, the hydro generator can go bankrupt. In simple terms, This defines an externality undesirable in a market, in which the errors of an agent can be paid by other agents. The golden rule is everyone pays for its own mistakes and takes advantage of their right decisions. The situation of thermal generators is different. For the planning period analyzed, the costs of top contracts cannot be recovered. The financial damage will be greater if the decision handling is not based on specialized mathematical management models. The graph indicates a general crisis of the thermal generators, if the top indicated by the government are signed. The graph shows that the financial health of a specific thermal generator may depend on its management capacity, and that if there is an exit, the generator can become profitable in a market in difficulties. High power allows Oil Express to financially analyze all market participants, both potential customers and clients of the competitors, which allows Oil Express to perform the scientific market intelligence activities. Considering that the proposal of tops made by government entities does not come from an optimization process, but were defined considering logic and good practices, Hale and Oil Express proceeded to make an adjustment in the value of the tops, so that they approached an optimal value, and thus analyze the behavior of the market in these conditions. These adjusted values do not come from an optimization process. However, it should be noted that the high-power model can be used to determine optimal top values. The graph presents the comparison of the results for the cost recovery of hydraulic generators. Values set based on mental rules can affect the market, even bankrupting it. It could be concluded that the greatest damage that can be done to the market is to establish reference values without justified mathematical support. Since there are values of the tops that minimize the values of the risk premiums for reliability, without profoundly altering the economic behavior of the market. It is coherent that if the thermal generators act rationally, they do not drastically affect the hydraulic generators as a consequence of their bad decisions. In the case of cost recovery of thermal generators, the situation is more complicated, due including the optimal values for the tops will generate problems of bankruptcy and liquidity, which will be more serious if the top values do not have an appropriate rationality. This indicates that the electricity market cannot guarantee that thermal generators can pay the top contracts that are theoretically required by the government. The model turned out to be correct, since in early 1998 it detected the market crisis between 1998 and 2000, which led to bankruptcies of thermal generation companies. Successful decisions. For its part, Oil Express has proven that there are no market conditions, that is, do not exist a good set profitable thermal generators that can pay for gas through tops contracts, required to guarantee the extraction of natural gas. If it is a question of compensating the situation based on price, if Oil Express sells natural gas at high prices, it is possible that Oil Express must recover bankrupt industrial company assets. Everything seems to indicate that the optimal decision may be to delay the investment, waiting for a market with better conditions. Successful decisions. For its part, Oil Express has proven that there are no market conditions, that is, do not exist a good set profitable thermal generators that can pay for gas through tops contracts, required to guarantee the extraction of natural gas. If it is a question of compensating the situation based on price, if Oil Express sells natural gas at high prices, it is possible that Oil Express must recover bankrupt industrial company assets. Everything seems to indicate that the optimal decision may be to delay the investment, waiting for a market with better conditions. Success case, China National Petroleum Corporation. The paper Operations Research Enables Better Planning of Natural Gas presents the use of mathematical optimization models for pipeline planning. China's natural gas consumption has nearly doubled in the past 5 years. To better meet demand, the China National Petroleum Corporation, CNPC, China's largest producer and supplier of oil and natural gas, partnered with researchers from the University of California in Berkeley and Tsinghua University in Beijing to apply operations research to develop and implement new software to help CNPC to improve the management of its pipeline network. Previously, all pipeline production and construction planning for CNPC, which controls 72% of the country's natural gas resources and 70% of its pipeline network, was done by traditional methods using spreadsheets. However, due to the increasing size and complexity of the network, The use of the traditional method resulted in excessive costs and wasted resources. Since implementing the new software, which uses a three-stage convex relaxation method, and iterative piecewise linear approximation methods, in late 2014, CNPC has obtained approximately $530 million of American dollars in increased earnings, 2015 to 2017. In addition, the resulting increase in the efficiency of the existing pipeline network allowed the company to postpone the addition of new pipes, leading to an official budget reduction of more than $20 billion of American dollars in construction costs for the following 5 years. The image present the algebraic formulation of the natural gas pipeline transmission model. Without fear of being wrong, it can be said that mathematical optimization models are the goose that lays the golden eggs of China National Petroleum Corporation. Like Herbert Simon, Hypothalamus Artificial Intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.